In this video series, we are talking about categorical data analysis, and we've started out with an example in which we have one explanatory variable that is categorical with two levels, and one quantitative response variable that is categorical also with two levels. So we looked at that example with aspirin versus placebo to see if it had an influence on the number of heart attacks that were encountered by these physicians who actually took the aspirin or the placebo over some period of time, such as 5 years. And we looked descriptively, and it looked like there was a little bit of difference, but a little bit of difference in this context could be important. But now we want to see if that difference is stable enough so that we can infer it outside of our sample of data. This is the omnibus hypothesis here. The omnibus hypothesis is that each category in each group has an equal proportion across the groups. So let's think about what that means in the context of our aspirin placebo example. Each category in each group. Well, what are the groups? There are two groups, two samples, as it were, representing two different populations. One sample represents the population of individuals not getting a treatment. So that would be the placebo group. The other group is the aspirin group, and that represents the population of individuals who could be treated by taking aspirin each day. So this omnibus hypothesis is that each category in each of these groups has an equal proportion. So what are the categories in the placebo group? They're yes or no. Heart attack or no heart attack. What are the categories in the aspirin group? They're yes or no. Heart attack or no heart attack. The omnibus hypothesis here is stating that the proportion of those in the placebo group who have a heart attack is equal to the proportion in the aspirin group, and the proportion of those who do not have a heart attack in the placebo group is equal to the proportion of those who do not have a heart attack in the aspirin group. Since we only have two populations, aspirin and no aspirin, and since we only have two outcomes, heart attack or no heart attack, this is really just the same as saying the proportion who have a heart attack in the placebo group is equal to the proportion who have a heart attack in the aspirin group. That is, it's just a test of the equality of two proportions, something you've probably encountered in the past, probably even in your first statistics course. If the proportion who have a heart attack in the placebo is equal to the proportion who have a heart attack in the aspirin group, well, then the other level of the category is automatically going to be equal. The proportion who does not have a heart attack in the placebo will be equal to the proportion who does not have a heart attack in the aspirin group. So in this 2x2 example, that is two groups and two levels of responses for each group, we're really only comparing two proportions. But once we get bigger, once we have more groups or more response categories, this is going to expand out and become more like this bigger picture you're seeing here. But in this case, we're really only looking at pi, that is the proportion in the population. That's what the Greek letter pi stands for here. We're really only looking to see if pi 1,1 equals pi 1,2, and if pi 2,1 equals pi 2,2. That's it. So the matrix is much smaller than what you're seeing here, but I've written it here in general terms so that you can take any number of groups, and I've indicated that with a capital K, or any number of response categories, and I've indicated that with a capital J. So in this case, we only have pi 1,1 equals pi 1,2, and pi 2,1 equals pi 2,2. Because we only have two groups and two levels of the response category. Now, how do we test this omnibus hypothesis? First, we have to meet certain conditions for valid inference. The observations within each category must be independent of the other observations in that category. So we have the common condition of independence of our participants. And furthermore, the observations must be independent of observations in other categories. I've seen this violated sometimes even in published research literature, where individuals might be asked to check all the categories that apply, and then they're put into a contingency table. Well, if you're taking a survey in which you check all the categories that apply, that means that you could be in more than one cell. And so in that case, you would not be able to use that contingency table and that data in order to make an inference using the method that we're looking at here. So the conditions for valid inference include not only that observations are independent of one another within a combination of group and response, but also across the various responses. You can only pick one response. So we would have to change that survey. Instead of check all that apply, perhaps say something like check the one that most applies in order to be able to use this method. At least 80% of the cells should have an expected frequency of at least 5. Why is that? Well, that's because we're going to use a mathematical distribution in order to model our test statistic. And you've seen this before. When you hear rules of thumb like you should have at least 30 in order to make sure that the sampling distribution is normal, that's the same sort of thing here. Here we're saying that at least 80% of the cells need to have an expected frequency of at least 5. And then similarly, another rule to make sure that we have a big enough sample size is none of the cells should have an expected frequency less than 1. Now you might be asking, what do you mean by expected frequency? We're going to look at that in an example in just a moment. So keep this rule in mind when we look at the example, that when we look at expected frequencies, 80% of the cells need to be at least 5, and none of the cells should have an expected frequency of 0 or anything less than 1. Now let's talk about testing the omnibus hypothesis. If populations have equal proportions, and that's what the omnibus hypothesis says, then the proportion in each category should be close to the marginal proportion. The marginal proportion, as you'll see, is how we're going to calculate our expected frequencies. And those marginal proportions are going to indicate what the proportions in each group should look like if the null hypothesis is true. That is, if there is no difference in the proportion of responses for each of our groups. We use as our test statistic x squared. It's a statistic to measure the difference between expected and observed frequencies. So x squared is going to be the sum of our observations minus what we expect under the null hypothesis. That means if the null hypothesis is true, we're going to look at the difference of what we observe and what we expect under the null. Well, what would that show us? If we're looking at an observation that is close to what we expect under the null hypothesis, that lends more credibility to the null hypothesis than if we get observations that are very different from what we expect if the null hypothesis is true. We take that and square that and then divide by the expected. Why square? To get rid of the negative signs. That is, whether we have a lot of difference because the expected is a lot bigger than the observed, in which case we would get a negative sign here, or whether we have a difference because the expected is a lot smaller than the observed, in which we'd have a positive sign here. We don't care about whether it's negative or positive, so we're going to square that. We're going to divide by expected. Now, when the omnibus null hypothesis is true, we know the distribution of that x squared is going to be approximately a chi-square distribution. There's our mathematical distribution that I referred to. with j minus 1 and k minus 1 degrees of freedom. That is j minus 1 times k minus 1 degrees of freedom. Just a single number. Remember, j, capital J, is the number of response categories, and capital K is the number of groups. So in our aspirin placebo example, we have 2 response categories, heart attack or not. So j is 2, and 2 groups, placebo or aspirin, and so our k is 2. So we would end up with 2 minus 1 or 1 times 2 minus 1 or 1. 1 times 1 is 1. That would be the degrees of freedom in that example. All right, so let's look at testing the equality of the proportions, that is the homogeneity. Remember, this is a model of homogeneity. Let's test for the homogeneity of proportions in our groups using the aspirin example. This will help clarify the conditions for valid inference as well as the method for testing the omnibus null hypothesis. So to get us primed for doing the hypothesis test, let's quickly review what we looked at in the last video. We have a placebo group in which 1.7% of the physicians had a heart attack, and we had an aspirin group in which a little less than 1%, 0.9% of the physicians had a heart attack. And we pictured that with these box plots. So again, the null hypothesis here is that despite these differences in our sample, we're proposing for the null hypothesis that in the population, there would be no difference. And that would be another way of saying aspirin doesn't do anything. So we are going to hypothesize no difference in the proportion of heart attacks in the aspirin and placebo groups in the population if we were to take this outside of our study. Now let's go back here and look at our original table of frequencies in order to see that we've met the conditions for valid inference. You'll remember that the first 2 conditions had to do with independence. Independence within groups and independence across groups. That means that for the placebo group, they have to be not only independent of each other in that group, but also they cannot appear also in the aspirin group. So they can't be in both. They're either in the placebo or in the aspirin, and the individuals were selected independently of one another. Now, these are all design characteristics, so I can't statistically see if we've met that condition for valid inference. Let's assume that we have, and in fact, I think that it's safe to assume that these physicians were taken independently of one another. Remember, there are 22,000 of them. And also that I know that those who got the placebo did not get the aspirin and vice versa. The other condition is to make sure that at least 80% of our cells have a frequency greater than 5. But it's not this frequency, it's the expected frequency. So we're going to have to calculate the expected frequencies first, and then we'll see if those are greater than 5 and that none of the expected frequencies are under 1. But I'm showing you this table because this gives me a pretty good indication that my expected frequencies are going to be in fine shape, because I have a fairly large sample here. Now, ultimately, we're going to calculate x squared, but there's going to be a shortcut for doing this, but I want to take you through, for understanding purposes, I want to take you through all the steps here. So let's look at the totals for the 2 conditions in the table. And so here's for the first condition, placebo, there's 11,000, and for the aspirin, there's 11,000. Let's look at the totals for responses. We had 293 yeses, 21,778 no's. So those are the totals. In other words, ignoring up here, ignoring whether they said or whether they had a heart attack or not. I was going to say whether they said yes or no, but no, it's not saying yes or no. It's whether or not they had a heart attack. And down here, ignoring whether they're in the placebo or aspirin group. Here's how many heart attacks we had, 293 for everyone in the study, 293. And if we take the overall total, we get 22,071. So why am I calculating those, what we call marginal totals? Marginal totals mean we're not looking at the individual cells, we're not conditioning on those cells, we're looking overall what kind of margins we had, what kind of totals we had for placebo and aspirin, response or heart attack, yes, heart attack, no, and overall. We're doing that because if there is no difference in the heart attack rate with placebo and aspirin in the population. We know there's a difference in our sample, but if there's no difference in the population, what is the best estimate that I can get of the proportion of heart attacks? The best estimate I could get would be to ignore whether they're in the placebo or aspirin condition and just look at the number of heart attacks, and then to get a proportion of it, look at the number of heart attacks out of the total. So that's what I'm doing down here. If placebo and aspirin in the population have the same number of heart attacks, I can ignore whether people are in the placebo or aspirin group and focus instead on the marginal totals, and that would give me a 0.013, so 1.3%. So I would simply say that the probability of a heart attack, or the proportion of those who will have a heart attack in the population, is 1.3%. Not whether they were in the aspirin or placebo group, just in general. And that's my best guess of what it would be in either of those groups if there was no effect of aspirin. All right, so if there's no difference in how our two conditions influence the number of heart attacks, aspirin isn't helpful, so the null hypothesis is true. We expect the same proportion of heart attacks to occur in both the placebo and aspirin conditions. And so here's the number of heart attacks I expect in the placebo condition. What am I doing here? I'm taking the proportion I just calculated, 293 over the total number in the sample, 22,071, and I'm multiplying it by the number that's in the placebo group. Way back up here, we calculate it. That's how many in the placebo. And that will give me how many heart attacks I expect if aspirin does not have an effect. Similarly, doing the same thing for the aspirin condition, multiplying it by the number that are in the aspirin condition, that's how many I expect to have a heart attack in the aspirin condition. So 146.48 up here. Obviously, we can't have 146.48 physicians having a heart attack. This is more of a mathematical thing. We're not taking a half of a physician. So basically it's 146, but we'll leave those decimal points in there for mathematical purposes. But basically we're saying 146. Similarly here, it's about 146 and just over a half, so about 147 if I round. So 146 in one group, 147 in the other, but we're going to go ahead and leave the decimal point in there. So what I've just calculated based upon the margins in my sample is I've calculated what my expectation was if aspirin is not going to be helpful. So notice that we could actually put these, I'm going to put these in as the null hypothesis, and here's the number of people that we expect to avoid heart attacks in the placebo condition if the null is true, and here's the number we expect to avoid heart attack, that is no heart attack, in the aspirin group. So again, if aspirin doesn't have an effect. So I now have expected values. I have 4 of them. Why 4? Because I have 4 cells. So I have, here's the placebo heart attack, here's the aspirin heart attack, here's the placebo no heart attack, here's the aspirin no heart attack, And so we have the 4 expected frequencies for those 4 cells. And remember that we need for at least 80% of these to be above 5. Well, they're all well above 5. And we need for none of these to be below 1. And obviously none of them are below 1. We're good. We have met the conditions for valid inference, assuming that we have independence of all the observations, both within and between conditions, but that is a design characteristic that we can't check with these numbers. So I now can calculate x squared, and look at how I'm doing it. I'm taking what I actually observed in a cell. I'm using the matrix notation here, so this is row 1, column 1. I'm taking what I actually observed in the heart attack condition for placebo, subtracting the expected value if the null hypothesis is true. Observed minus expected. The more different they are, the more I would tend to believe that the null hypothesis is not true. The more alike they are, the closer this will be to 0. In fact, if this observed and this expected under the omnibus hypothesis, if they were exactly the same, and that was true with every cell, I would get 0 for my x squared. So the smallest possible value I can get for x squared is 0, but the bigger x squared gets, the more evidence I have that the null hypothesis is not true. So we ended up with 25 when we took observed minus expected squared divided by expected, we got 25. Now, what is that 25? I've got to do 25 relative to something. What we're going to do it relative to is the chi-square distribution. So I'm going to see where this falls on a chi-square distribution. So where does it fall? It falls way out in the tail of the distribution so that over 99% of the area is to the left. Well, if I want to get the p-value, I do as extreme as x squared or even more extreme. That is, I need to take 1 minus that probability, and there's my p-value, a tiny, tiny number, almost 0. 0.0000005, or 6 if I round. So 0.00000, I don't know if I said enough zeros there, 6. So the p-value is very small. Now, all of that above was just to show you how everything works. Do we need to go through all this? As you might surmise, no, we have R. R can do calculations for us. So if I put my heart table, remember I created a table called heart. If I put my heart table and use the summary command, the same command I use for a 5-number summary, except that this is being used for a categorical variable. That is 2 categorical variables, actually, categorical condition and categorical response. If I use the summary command with that, look what it gives me. It tells me what my sample size was, tells me how many different groups I had, and it gives me my x squared and tells me the p-value, the probability. So in that one swoop, I did everything that I did up here, but I did the up here so that you could understand what I was talking about when I was talking about on this slide, the observed minus expected. Observed, that makes sense. It's what we actually see. We have 4 cells. What do we see in the first cell? That's our observed. But what did we expect in that first cell if the null hypothesis is true and there's no effective aspirin? That's what we calculated, and ultimately what we had R calculate in one fell swoop there at the end. So that's how we make inferences about the omnibus null hypothesis. And that omnibus null hypothesis is the only one we have. Why? Because we only have 2 groups and 2 response categories. So the question is, does aspirin work or not? And the answer is, it appears that it does. And as a result of this study, taking baby aspirin every day became a big thing for a while. Not so much anymore because there's been some contradictory evidence that came out, but for a while, it was after these study results were released, baby aspirin was bottled and put on shelves, and little small doses of aspirin with sometimes little heart symbols on the label, and people would take aspirin once a day in order to try to reduce the chance of heart attack. So in this study, we were able to reject the null hypothesis of no effect of aspirin and found that aspirin had an effect. Now we need to move beyond 2 groups and beyond 2 response categories, so we'll do that in the next video.